So, now that we've explored the basics of deep learning, let's delve into what catalyzed the modern era of deep learning. Three key technical forces have driven this transformative period: hardware, data, and algorithms. These elements converge around the year 2012, marking a pivotal moment in the history of artificial intelligence. This convergence set the stage for significant breakthroughs across various industries. First, let's discuss hardware. At its core, a computer is essentially a highly capable calculator. The central processing unit, or the CPU, which is the main part of a computer responsible for carrying out instructions, has seen tremendous advancements. Between 1990 and 2010, within the 20 years, we witnessed a staggering 5,000-fold improvement in computational speed. This exponential increase in processing power has enabled computers to handle a lot more complex mathematical models, making it easier to work with big sets of data and solve more complicated problems. So, the computational power of a single chip has been ever growing, but with the discovery of GPUs, or graphics processing units, have been around for a while, primarily used for image processing, video processing, and gaming. They weren't initially developed for deep learning. If you've ever been into gaming, you might know that to run high-spec games, you definitely need a good GPU. So, GPUs have evolved significantly thanks to demands from the gaming and processing industries. As these technologies advanced, GPUs became more powerful and versatile, meeting the increasing requirements of high-resolution games. Now, let's compare CPUs and GPUs. CPUs are like fast processors with few bigger chips that can handle a limited number of operations at once, typically up to 8 cores. This architecture makes CPUs well suited for tasks that require quick sequential data processing and complex decision making. On the other hand, GPUs consist of many smaller chips working in parallel. Each of these chips has a slower individual computational speed, but combined, they can handle many tasks simultaneously, making them perfect for the massive parallel processing required in deep learning. So, we'll give an example of a game. In the context of gaming, where you need to simulate an entire virtual reality, handling physics, sound, and video simultaneously, CPUs fall short because they excel at processing tasks one at a time rather than in parallel. To overcome this, GPUs employ a different approach, packing many smaller chips that work together to handle multiple tasks at once. This architecture is much better suited for the parallel processing demands of modern games. Imagine in a game, a player shoots a bullet. With GPU acceleration, not only can you see the bullet flying in real time, but you also observe its interaction with the environment. The bullet may ricochet off surfaces, break objects, or kick off dust, all rendered dynamically with complex physics calculation that GPUs handle efficiently. When exploring vast game worlds, moving from one area to another often requires loading new maps or scenes. GPUs excel in this area by swiftly rendering new environments as you traverse different zones. This capability ensures a seamless visual transition, with minimal loading times and no disruption to the gameplay experience. So, how did GPUs, initially prominent in the gaming industry, become a powerhouse in deep learning? In deep learning, as we've discussed, the architecture typically involves layers of neurons. Each neuron performs relatively simple calculations, such as solving linear equations. While each neuron's task is simple on its own, the real challenge lies in the cumulative demand when scaling up to the vast networks typical in deep learning applications. For a CPU, handling a single neuron's calculation is straightforward, but the challenge arises with the sheer number of these calculations needed across thousands or millions of neurons. In contrast, GPUs are adept at managing these tasks. Much like handling multiple elements in a game simultaneously, be it physics, sound, or video, GPUs can process numerous neurons or even entire layers simultaneously on different chips. This capability makes GPUs incredibly efficient for the parallel processing demands of neural networks. This efficiency allows for faster development and more sophisticated deep learning models. Since the adoption of GPUs in deep learning, there has been a noticeable spotlight on their performance. What used to be a slow and tedious process with CPUs has become much faster and more efficient with GPUs. The transformation was particularly evident with breakthrough applications such as ImageNet, where GPUs were used to significantly accelerate the training of deep neural networks. Previous research had already pointed to the potential of GPU multiprocessing, but it was their specific application in tasks like ImageNet that demonstrated dramatic improvements in performance. This success has inspired further research and investment, solidifying GPUs as a critical tool in the advancement of artificial intelligence technologies. So, NVIDIA has transcended its role in the gaming industry to become a key player in the artificial intelligence industry as well. They have developed CUDA, a GPU programming interface, which has become a cornerstone in the development of the hardware aspects of AI. To summarize, CPUs have increased in speed individually over time. Then, by assembling many of these processes together, we created GPUs. These GPUs have proven to be incredibly useful in deep learning, significantly enhancing performance and efficiency. The second driving force is data. Machine learning and deep learning heavily rely on an abundance of data, often described as the fuel of these technologies. It's not just about having large amounts of data, but also about having refined data. For instance, video data might need adjustments like fixing image size and channel formatting. Before the internet, each institution typically maintained its own data structure, which made large-scale data sharing and standardization difficult. However, with the advent of the internet, platforms like YouTube have standardized the format of their videos. Similarly, Wikipedia provides information in a consistent format, simplifying the process of refining data for machine learning applications. The development of the internet has therefore significantly increased the supply of refined data. The increase in refined data, made possible by the internet, paved the way for the next big step in data management and accessibility. As the amount of data continued to grow, the need for better storage and processing solutions became more apparent. In recent times, cloud services have become incredibly prevalent. Platforms like Google Cloud, AWS, and Microsoft Azure offer robust cloud computing services that facilitate the storage, processing, and analysis of vast datasets. Another key example is ImageNet, which has compiled over 1 million images labeled across 1,000 categories, collected primarily from Google. This platform has been instrumental in advancing deep learning algorithms by providing a massive, accessible dataset. By offering an extensive collection of labeled images, it enables researchers and developers to train sophisticated neural networks more effectively and efficiently. The diverse range of categories and high volume of examples helps these algorithms improve their accuracy and adaptability. On top of technical advances in hardware and data, researchers have developed algorithms that optimize neural network performance, enabling them to learn faster and more effectively. These advancements didn't happen separately. Instead, they worked together, each enhancing the overall progress and impact in the field of AI. Some of these key improvements include enhanced neural network algorithms, to mention a few, which will be discussed later, such as activation functions, weight initialization, and sophisticated optimization techniques like ATOM and RMS prop. These improvements in the field began to coalesce around 2009 and 2010, coinciding with the launch of ImageNet. This period marked significant progress in deep learning. For instance, in 2012, the deep learning field saw groundbreaking development with the introduction of AlexNet, which dramatically improved the capabilities of neural networks, setting off a wave of deep learning advancements. Following this, in 2016, the success of AlphaGo, developed by Google DeepMind, demonstrated the practical impact of these advancements in AI by defeating a professional human Go player. More recently, the development of AI models like ChatGPT and applications like Sora have continued to showcase the rapid progress and broadening applications of deep learning techniques. Now that we've established a fundamental understanding of artificial intelligence, let's briefly discuss the different types of AI by learning methods. There are 3 types of AI by learning methods, and we'll talk about what learning methods are, and they are supervised, unsupervised, and reinforcement learning. We'll delve into what each of these entails. To start with supervised learning, think of it in terms similar to how a professor supervises graduate students. Just like how a professor provides specific guidance, feedback, and corrections to students based on their particular task or assignments, in supervised learning, the teacher role is played by the dataset. For example, if we input a picture of a cat, we also provide the correct answer, or a label, such as the coordinates containing the cat. Essentially, supervised learning involves feeding the model both the input and the label. This pairing of input and label allows the learning model to use these examples to understand and predict the correct output for each given input accurately, refining its ability over time, much like a student gradually becomes more adept under the guidance of their professor. Now, moving on to unsupervised learning. This method is used when the data does not have explicit label, or when the input and the label are the same. Now, we'll go more in depth on the differences between supervised and unsupervised learning, 2 fundamental divisions within machine learning. Supervised learning involves training a model on a labeled dataset, where each input data point is paired with the correct output. This method is similar to learning with clear guidance. Each training example tells the model precisely what the output should be for a given input, making it ideal for tasks like classification and regression, where the correct answers are known. So, in the case of supervised learning and the task of classifying different breeds of dogs, we could use features such as color and size to classify each data point to a specific breed of dog. In supervised learning, the model looks at the distribution of these features within the dataset. Based on this analysis, it draws a line, or more technically, a decision boundary on the graph. This boundary helps to distinguish and classify sets of data points into categories corresponding to different breeds of dogs based on their features such as color and size. However, it is important to recognize that this decision boundary is not always perfect. Due to the inherent variability and overlap in real-world data, some data points might be misclassified. This imperfection is a natural aspect of statistics, where decisions are made based on probabilities and trends rather than absolutes. Thus, while the decision boundary provides a useful framework for making predictions, it cannot guarantee perfect accuracy every time. So, to restate what supervised learning is, it is about training a model using a dataset where every input is explicitly paired with the correct output, allowing the model to learn and predict outcomes based on known examples. Unlike supervised learning, we don't provide the label in unsupervised learning. Rather, we look at the distribution within the data and attempt to cluster. So, we don't give the model any information such as what breeds each of these data points represents. In the case of tasks like classification, unsupervised learning might involve clustering data based on inherent patterns without predefined labels. For example, programmers might use features like color and size to differentiate between 2 breeds of dogs. However, unlike supervised learning, which relies on labeled data to draw statistical distinctions, unsupervised learning uses the data's natural distribution to form clusters. To make this more intuitive, Let's consider some pictures of birds. I don't know these birds, but using the human intuition, you might group them based on similar features like color or beak length. Then, we will be able to cluster these birds into the same breeds. These two birds are both brown and have small beak, so they should be of the same species. And these two, which are both red and have the long beak, are likely of the same species. And the following two, based on the pattern on their body, they're likely of the same species. And these two, based on their color, beak length, and neck length, are likely of the same species. So using the human intuition, we can cluster them into different groups based on the characteristics that we can observe. In this case, a computer would use algorithms to examine the features of each bird, such as color, size, and shape, and then autonomously organize these birds into clusters that share common traits. This method of feature extraction and clustering allows the machine to learn and make sense of the data itself, mimicking the way humans might naturally categorize objects based on their observations. Lastly, there's reinforcement learning, which might recognize from applications like AlphaGo. Unlike supervised and unsupervised learning that primarily focus on classification or clustering, reinforcement learning involves an AI developing strategies to solve problems. This method centers around the concept of making sequential decisions. The AI learns to perform actions based on feedback from the environment to maximize some notion of cumulative reward. Here's a brief explanation. In an environment like a game, the AI agent learns to maximize its rewards. In AlphaGo, the game state provides the environment information, the players are the agents, and each move is an action aimed at increasing the likelihood of winning. This learning process, which focuses on optimizing decisions over time for the best possible outcome, is what we call reinforcement learning. As reinforcement learning has evolved, it has grown increasingly sophisticated, incorporating complex strategies that go beyond simple win maximization to include long-term planning, risk assessment, and adaptation to changing environments. These capabilities have not only proven effective in board games, but also being explored for potential applications in robotics, autonomous driving, and resource management, where decision-making in dynamic environments is crucial. Let's take a look at the medical industry, in which I'm in. While current AI might classify X-rays or cluster chemicals, reinforcement learnings could potentially automate entire medical procedures. By analyzing cycles of a procedure, it could suggest the optimal treatment plan to maximize patient survival rates. In finance, reinforcement learning can be employed to develop automated trading systems that learn to make trades based on patterns identified from historical data, aiming to maximize returns and minimize risks. Furthermore, in the field of logistics, reinforcement learning can optimize supply chain processes by determining the most efficient routes and schedules, reducing costs, and improving service delivery. These examples showcase the versatility of reinforcement learning in adapting and finding solutions to complex, dynamic problems across various domains. The historical development of reinforcement learning as a field within artificial intelligence has been marked by several key milestones. Initially conceptualized in the early 1980s, the approach was influenced by studies of animal learning psychology, particularly the processes involving decision-making and reward systems. The introduction of Markov decision process framework provided a mathematical foundation for modeling decision-making in environments with stochastic outcomes. To go back to a point made earlier about unsupervised learning, we said that the input itself serves as a label. This approach is referred to as self-supervised learning. This concept bridges some of the gaps between supervised and unsupervised learning by using the data itself to generate its labels, which the model then learns to predict. So, the takeaway is that artificial intelligence algorithms can be categorized into supervised, unsupervised, and reinforcement learning.